Welcome to the course introduction of 1DV607 Object-Oriented Analysis and Design using UML. In this lecture I will try to place the topic in the everyday life of a developer, explain what analysis and design is really about and what object orientation is. It's not meant as an replacement for the chapters in the book, so read the book, the course literature, and use these materials as a complement. So maybe then first of all we should place analysis and design in the everyday life of a software developer, but then maybe the question becomes, what is software development? You can think about this for a few minutes and try to think about your own definition of software development. What is software development for you? There are probably many definitions going around, but think about it for a little bit and I will present mine. So when I think about software development, I think about people collaborating. So as a software developer, you need to collaborate with a lot of different people. So of course your co-worker, your fellow developers are people that you need to collaborate with, and also you need to collaborate with other developers that make the libraries that you use, that make the modules that you import into your project. You need to collaborate with them and understand how their libraries are supposed to be used. You also need to collaborate with end users to understand what they want from the software or what the market wants from your software. So collaboration is important, I think, one of the fundamental aspects of professional software development, at least. I also think that when you do software development, you create something new, something that has not really existed before. Maybe it's new for you in your little world, but it can also be something that is really novel and new. If you're working on a new feature, for example, in a software, it's something that has not existed before, really. If software development was just manufacturing, we would just copy software, and if there was no novelty in our software, it would be easier to just copy an already existing software, because that is essentially free. We also need to have a need for the software that we develop. So someone, maybe ourselves or a market, or maybe you even have a customer or end user for your software. So they have a problem, you need to fulfill this problem. You need to solve this problem for them. And I also think that another key aspect here is that the world of software development is rapidly changing. We have new methods, we have new libraries, we have new technologies, we have new platforms, we have everything is changing, and the requirements for our software, the needs that need to be fulfilled, are also forever changing. So my definition of software development is the collaborative creation of software that fulfills a need in a novel way in a rapidly changing environment. Maybe not the best definition, but it's my definition at least. So now that we know what software is, kind of at least, we need to have a way to manage this creation, this novel creation in a rapidly changing environment, and we need to be able to collaborate with a lot of people. So it's not that easy to develop software, it's quite complex, and to handle complex things we need some form of process. So my next question is, what do you think that you will do at work? So you will graduate here in maybe 2 or 3 years. What do you think a working day will be like? What will you actually do? Or what would you like to do? Maybe that is a better question. You can take a few minutes and think about that. So basically, I hope that you answered something about programming or coding that you would like to solve problems, and by implementing, by programming, because that's what your education is a lot about, I think. But in order to be able to know what to program, you cannot just randomly write if statements, I guess, even though it could be a fun exercise. You need to have some kind of idea of what it is that this software that you are supposed to implement is supposed to do. What are the requirements of the software? What's the problem here that's supposed to be solved? In some cases, the problem is also not trivial. It's maybe an area that you're not familiar with. Maybe it's a banking software that you're supposed to develop, and you need to understand everything about stock markets and option trades and interest rates and different types of accounts and a lot of laws and regulations and things. So you need to understand this area also that you're supposed to work in. So you do some requirements to understand what it is you're supposed to do. You do some analysis to understand the problem area. And when you have understood the problem area to some degree at least, then you can start thinking about, all right, how do we solve this from a technical standpoint? Maybe you are 50 programmers. How can we develop this software efficiently using 50 programmers? Maybe you are 5 programmers. Then you have other needs for a technical solution maybe. What libraries are you supposed to use, and how are they supposed to work together with your implementation? So you need to have some common ground of the technical solution in order to be able to implement things efficiently. Then of course you need to test, and you need to ship the software to your end users in some way. And of course you will be Googling Stack Overflow and struggling with Git in the process here. Hopefully having a lot of coffee and fika also. So this process, the basic development process that you can find in many areas, is requirements, analysis, design, implementation, test, and deployment. And if you do this one step after the other, it's called the waterfall model. We won't be talking really anymore about that because it's an ancient model that doesn't really work that well for software just because of this rapid changing environment. Instead, we have been focusing on iterative and incremental models the recent years. It's you can find a lot of different processes that has at heart the idea of an incremental and iterative development. Scrum, Kanban, unified process, whatnot. The idea is that you work with all of these activities a little bit every day during your working time in the project. So do a little bit of requirements, a little bit of analysis and design, a little bit of implementation, a little bit of testing and deployment. So instead of doing all the requirements first, we do what's important first, and we add things later as we go along, and we change maybe things as we understand the problem better, because we have deployed it to the end users so they can try it and they can give us feedback, so we can iteratively, incrementally grow the system over the time of the project. This has proven to be a much more successful way of developing software. So you come into your office, you sit down, and the first thing you need to do is figure out what to do that day. So you need to read some requirements, work something with the requirements. You need to understand the requirements, know how they fit into your overall understanding of the problem that you are working on. So you work a little bit with requirements, you work a little bit with analysis. Then you need to understand, how am I supposed to implement this? So you need to understand the technical aspects of the software you are working on also. How does this feature fit in? What is the most efficient way I can implement this without destroying something else, without impacting some other part of the system? So you work a little bit with design, and maybe now it's time for the first fika break, and you head off to the coffee room and you discuss these things with your fellow developers and kind of get some feedback on your ideas for how to implement this. And maybe you discover that you have misunderstood something about the problem, and it's really not supposed to be in that way. And maybe you even need to call up your end user and ask them about the requirement, or the product manager about the requirement, or something like that. Anyway, after the fika, you feel more secure about your technical solution, so you do some implementation. And you write some test cases also to support this implementation, so that you know that you are not breaking anything, and you know that your feature at least works on your computer before you commit it to your branch, and you integrate the branch in a merge request, and it finally gets deployed towards the end of the day to the end users. And so on and so forth. The system incrementally grows a little bit for every day that passes, and you work a little bit with requirements, analysis, design, implementation, test, and deployment every day. These shapes are supposed to communicate a little bit about the focus of each activity during the process. So in the beginning, it's naturally that you probably spend more time trying to understand a little bit more about the requirements and the analysis and maybe the technical solution, make some decisions here. During the middle of the project, there is a lot of implementation going on. Testing effort maybe becomes more and more towards the end, because there is more of the system to test, and vice versa with deployment. At least this is kind of like the traditional, a little bit blocky view that I have done in this slide, but you probably get the main idea here. Something that has happened in recent years is the automation of different steps in this process. So automation of deployment is quite common nowadays, and maybe that has skewed this diagram in some way. Maybe there is actually more effort for setting up the automatic deployment in the beginning of the project. This is more of a technical thing now than a manual, laborious thing. And also test automation has really come a long way in the last year. So maybe this diagram here is starting to look a little bit different, really. One thing that has happened quite recently with OpenAI is that they released a demo of their Codex implementation, that is automatic code generation based on natural language input. So you basically can tell the AI what you want from an implementation, and the AI produces the source code for you. So you don't need to Google Stack Overflow for doing these kind of mundane, boring tasks in implementation. You can just tell the AI, I would like this to happen in this function, and the AI will present the source code snippet to do that. This is really interesting, I think, and it actually shifts the focus from knowing the details of a programming language and how you really program these kind of boring functions that you often have. Kind of like 90% of programming is often more or less the same things over and over again, and can let us focus more on how are we actually going to do this in an efficient way, in a novel way. How are we going to solve the problem in a good way? So maybe this will shift focus even more towards analysis and design if implementation can be more or less automated. Interesting. We will see what happens in the coming years, I guess. So a little bit about analysis and design then. So in this course we will do domain modeling as analysis, and domain modeling is something that we can use to understand the problem better. We understand the requirements in a kind of a context. So we don't look at a requirement in isolation. We look at a bunch of requirements and try to create a model that can support these requirements, so we can understand the problem better. We can use a domain model to visualize and to communicate this understanding to someone else or to ourselves when we need a reminder of. We get a common vocabulary, we get a common set of rules for this domain, and maybe we can even reuse this in coming projects. For the design, we will create something called the design model, and basically it's a technical solution for the requirements that we are working on. So it's also something that we use a visual model for, and we use it for communication, so that we as developers can understand how we are going to collaborate, how we together are going to develop a software system that works, and so that we have common solutions, that so everyone can understand them. We have standards that we follow. So basically that's analysis and design. Analysis is what, design is how. So object orientation. It's basically a coherent way of doing analysis, design, and implementation using the same ideas, the same way of thinking about the problem. And this is very powerful because it creates a mapping from the requirements the entire way to the implementation, so we can find commonalities, so we can understand how the implementation works by knowing something about the problem domain, about the requirements, about reality. One of the main ideas about object orientation is also that it should support the human way of thinking about things, and basically this boils down to three things. It's abstraction. As humans, we like abstraction because that lets us focus on details when we need them and not add them when we don't. For example, I can ask someone to go and get a cup of coffee, and I don't need to tell that person the exact way to the coffee machine and the exact way to get the coffee, the exact mug to get, and things like that. Things that are not important should not need to be added. So this is something that object orientation supports. Object orientation also supports hierarchies. Basically, there are two types of hierarchies that we humans use. Whole and part hierarchies. That is, we construct things based on smaller things and we put these together, and we often slap an interface on the thing so that it can be useful at a high level of abstraction. We can, for example, imagine a car. A car is created using many different complicated parts that can hardly be understood in detail, at least by a single human anymore. But almost any human can use a car for what it's supposed to be used for. We can drive a car using this common interface of a steering wheel and some gear shifts and knobs and buttons. So abstraction and whole part hierarchies. Another way we use hierarchies as humans is this is a kind of hierarchy. So we understand that a dog is a kind of animal and a monkey is a kind of animal. And we can understand our reality based on these types of hierarchies that we quickly build inside our minds. Finally, we have the idea of encapsulation, that an object owns its own information of sorts. So if I ask someone to change his or her name, it's up to that person to do that. So I send basically a message to the object. Please change your name to something else. But it's up to that object to accept this or not. So as another object, I cannot interfere with the other object's information. It's encapsulated and owned by the object itself. This is also something that's supported and quite important in object orientation. So using object orientation, we can get a shared vision of a problem and a solution. We have this common vocabulary and we base this off reality. And object orientation is supposed to make things easier for you. If it makes things harder for you, you're probably not using it optimally. Throughout the course, we will be using a small subset of the unified modeling language. The UML is a visual modeling language where we create different diagrams showing our models visually. Visual modeling has an advantage in that we are quite visual beings and we like visual information, and we can spot strange things in visual images quite quickly. While looking at text, for example, we are not really that fast at reading. So we tend to focus on visual models so that we can show things to our peers or to ourselves in some time. We will be using a small subset, as I said. We will be doing class diagrams, object diagrams, and sequence diagrams. So It's not really that advanced, the language that we will be using. So let's take a small example. We start with a requirement because that's where we need to start. And this requirement is small and quite easy, and maybe by reading it you get this mental model inside your head of what this is all about. You get some idea of the items that are used in this small game and what's really happening here. Requirements are often behavioral, that is, they have some description of what is supposed to happen in a certain situation. Maybe they even have a flow of events that happen in sequence. So requirements describe the behavior of the system. To complement this behavioral view, we do the analysis, the domain model. So we create a structural or static view based on our requirements. In this case, we only have one requirement, so it's a little bit easy. But as you see here, we have made some decisions or found some problems in our requirements when we try to make this analysis. So we understand that we have player, we have a dice game, and we have dice classes. And these communicate with each other in some way, and we need to keep track of the dice inside the dice game, and we need to know the player that plays the dice game. But looking at the requirement, we don't really know that there are two dices and that the number of faces on the dice are 6 faces. It could be something else, of course, but when we build our mental model, it's quite easy to jump to conclusions and make assumptions. So doing the analysis, we can realize where we have done some assumptions, and typically this is a very good thing. If you find things that are wrong with your requirements while you do your analysis, you're doing it right. And then you need to go back to the requirement, understand it better, or ask the person that actually stated the requirement from the beginning. Are we supposed to use 2 dices? Are the dices supposed to have 6 faces? After we have understood the requirement, we have done our analysis, we can move on to designing the behavior of the system. And now we are talking about objects here, and we can see that we have 5 different objects: a program object, a player object, a dice game object, and 2 dice objects. The program object is a little bit special because we couldn't find a class for that object in the analysis. It's a technical kind of object that is needed for the program to work, and that's quite common for the design. Here we introduce software things that are not really part of the problem per se, but is part of the technical solution. You can see that the objects send messages to each other, and they send these messages in sequence, so that we have a sequence of messages that are sent to the objects so that the requirement can be fulfilled. For example, the dice game tells the dice to roll itself, and it collects the value from the dice, and it returns true or false based on this condition if the sum is 7. And the player outputs something on the screen for the end user to see. And we can also take a look at the structural design view here, a class diagram for the design. It's quite similar to the analysis in this case, maybe a little bit more detailed only because we have added these messages that needs to be sent between the objects so that the requirement can be fulfilled. What we can see here is that we have the same concepts in the requirements, in the analysis, in the design, both the behavioral and the static side of the design. So we get this advantage by thinking about objects, thinking about the classes of the objects. And of course also we have the implementation where we have the dice and the player and the dice game. So by having all of this, we get this mapping between the problem domain, between the problem area and the actual implementation. So how do we do this? Well, we use our experience. And if we don't have experience ourselves, we need to use guidelines, patterns, and principles. That is the experience of others. So this is basically what we will be doing in this course. We will be learning guidelines, patterns, and principles on how to create object-oriented models for analysis and design that then can be implemented and create a good implementation. A good implementation is something that we can discuss what that is, but typically we are talking about things that it should be easy to change. Changes should not affect other parts of the system that are not related to this change. We should be able to divide the work among several developers. We should be able to understand the system as a whole and as the individual parts. Object orientation has received a fair bit of criticism, and I think that's good, and in some cases the criticism is perfectly valid. This is not a comprehensive list of criticism, but some points that I like to discuss a little bit. So the first thing is that inheritance is hard to get right, and I agree with that statement. It is hard to do inheritance in a good way, and I also think that it has been downplayed quite a lot in recent design thinking when doing object-oriented designs. Basically in this course we will only use inheritance if we feel that we have some opportunity in the source code to do inheritance. We have some duplicated code in two classes that are common, they seem to have some common base, then we can create a new base class and inherit the common implementation from that. I think that's probably the best way to try to do inheritance. It's super hard to do inheritance from just analysis and design and not doing any implementation. So, well, object orientation is of course not a silver bullet. No method is a silver bullet, no process is a silver bullet, no language is a silver bullet. You can write perfectly bad programs in object-oriented programming languages. You can do perfectly bad designs even though you use the UML or this tool that you have. You need to be a good developer to develop good software, and you can only become a good developer by training. So just using a method will not save you in any way. Also, this thing about object orientation that it's supposed to mimic reality, well, it's not always all problems have a base in reality or are suitable for being implemented as they work in reality. Software is software, and it's special because it's soft. So in some cases it's maybe better, maybe from a performance standpoint, to do things differently and not do it as it works in reality. Can be a little bit of a lost opportunity if we are kind of like locked into how reality works, and that's how our software is also supposed to work. I think that's an interesting criticism to object orientation. Spending too much time on diagramming is of course a waste. Doing these detailed blueprints for the complete systems is not realistic to do in real projects, especially not in large software systems. You need to spend your time wisely and do the analysis and design of the parts that really matter, and especially if you're supposed to document this in a diagram, because doing diagrams takes a lot of time, and that time needs to be well spent. So think in reality, you need to think once and twice about what the purpose of the diagram is. I don't think time spent on analysis and design is a waste per se, and you always do analysis and design. Maybe you do it in your head. You do it in a discussion with your colleagues. Then you analyze and you design things. So I think this is a criticism towards the waterfall thinking about we need to do a complete blueprint over the whole system before implementation can start, kind of thing. Something that, some other thing that is quite tricky in object-oriented implementations or designs is state management. And this, I think, is because objects are most often shared between functions or methods. So if you send an object as a parameter to a method, it's actually a reference to an object that exists in memory. And if you send the same reference, those all point to the same object. And this can be a little bit tricky at times, because sometimes you don't want to do that. Sometimes you want to copy an object, and there is not always, it is not always clear on when you need to do a copy or when you can actually change the state of an object, and it can be tricky to manage that. And the confusion often gets even more so because you have these primitive data types often in object-oriented programming languages that are always copied. So objects are always references, primitive data types are always copied, and that's, well, a little bit strange to many. So you need to manage your state, even though you have this encapsulation and thing going on. You need to really try to use that as good as possible. So my goal is, of course, that you should become better developers by attending this course, and we will practice a lot of analysis, design, and implementation during the course. So that's it for now. Bye bye.